Good morning, this is FE Peer Review. The date is the 15th of December 2022. My favorite map projections number 3, the Mollweide projection, pseudocylindrical and non-conforming. We're going to look at both those properties in this video, and this is the reason why. In my previous video, projections number 2, we looked at the Lie-conformal mnemonic, and Sfera left a comment with a question that I thought was interesting. Don't all projections use lat long that are orthogonal? I responded, actually they don't. It just depends on how people choose to arrange them. And then I wrote, I found a perfect example. I'll work on it today. It's a good way to procrastinate. And here's the results of all that hard work I'm doing. This is the Mollweide projection, and it's called a pseudocylindrical projection, and it is non-conformal, which means that the latitude and longitude lines do not cross at right angles, at least everywhere except 1 or 2 spots on the plan, 3. So we have the Greenwich meridian right down the center, and we have the equator across the middle, and a beautiful ellipse. At each ends of the ellipse along the horizontal axis, the latitude and longitude lines do indeed cross at right angles. At the very center, they cross at right angles, but everywhere else, lat and long cross at other than right angles. And you can easily see that that's the case if you picture a tangent to any of these. What makes it cylindrical is that all the latitude lines are parallel lines. What makes it pseudo-cylindrical is that in order to make it an equal area map, which it is, it has to go to 0, the top and the bottom, which is not something you can accomplish in a cylindrical projection, and we'll take a look at that in a minute. Actually, let's go ahead and take a look at the basics of cylindrical projections right now. Britannica.com has a good page on the subject because it serves as the basis for the Mercator projection, which we will look at in the near future. But here is the basics on cylindrical projections. What we see in this diagram is on the left half of a globe. And that globe is, you can visualize that globe as being inside of a cylinder, a toilet paper tube or something. And then a point source of light at the center of the globe is casting the image of the surface of the globe onto the inside face of that cylinder. So the horizon, where the cylinder and the sphere touch, they meet perfectly, and there's no distortion. And then as you move up in latitude, the distortion increases until you get to the north and south poles, where it's infinite distortion. Well, now you've got your cylinder, you slice it somewhere convenient, and you unroll it, and you've got a nice flat surface. You've got parallel latitude lines and parallel longitude lines, but parallel longitude lines are the key that there's a problem, because at the north and south poles, all the longitudes converge. They're actually getting closer and closer together as you move away from the equator, and that is not shown on the map. So that's your key to the limitations of a cylindrical projection. So a pseudo-cylindrical projection tries to reduce some of that by, instead of putting it in a cylinder, it's putting it into a shape that converges at the top and bottom. But there you go, that's the Mollweide projection, and we're going to look at some of the distortions in it. So I'm going to fiddle with opacity here and gradually bring up an image which shows the distortions. We have our favorite little orange circles and ellipses, and these circles are all of the same area. I keep saying circles, but they're ellipses. These ellipses are all of the same area, but as you can see, they vary in shape. Their long and short axes are different, and this represents the kind of distortion we're seeing in the surface of the Earth's sphere as it's projected into this particular projection here. So if we were to zoom in at the equator, at the Greenwich meridian, there'd be 0 distortion. but as we are not that zoomed in, we're seeing a little bit of distortion. You can see extremes around the edges and less distortion in the middle. A couple of interesting little articles that discuss equal area maps. There's a Wikipedia page on the subject of equal area map projections. It says, in map projection, equal area maps preserve area measure, generally distorting shapes in order to do that. Equal area map projection cannot be conformal, nor can a conformal map projection be equal area. So that's a little something to keep in mind. You got to make your choice there, one or the other. There was a nice page at the City University of New York on maps, and I'm going to be coming back to this page for future videos for sure. There's a lot of material here, but it has this to say about equal area maps that's interesting too, very useful. Let's scroll up here. This map in the middle of the image here is an equal area map. Dot density maps show the concentration of an attribute in an area. So if you want to have a good map for that purpose, you want an equal area map to give the most accurate representation. The map of world population density that we see here uses one dot to represent every 1 million people. If areas are not in true proportion, the map will give false impressions. Countries that draw larger than their true area scale will look less dense than they should. Countries that draw smaller than their true area scale will look too dense. So they've used an equal area map because they're trying to show visually the population density, and in order to do that they need to have consistent surface areas represented. You know, whether the shapes are somewhat distorted is not important for their purposes, so long as the total area involved is correct. So that's a dot density map showing Earth's population, and it uses an equal area map for that purpose. So that's one reason why you might choose an equal area map. There's another very interesting article on ESRI's website, and there will be links to all this in the description. ESRI is I believe, the most important map making company in the world. Their material is used by everybody. So they have an article about the development of an equal area map projection that they call Equal Earth. And it came about because of political factors. So I'll read the highlights of the article. The Equal Earth projection was created in response to a wave of news stories in 2017 following the Boston Public Schools announcement that it was switching to the Gall-Peters projection for all classroom world maps. These articles erroneously asserted that the Gall-Peters projection was the only equal area projection that shows land features at their true relative sizes. Despite the consensus about inappropriateness of this projection for small-scale mapping. So some of you may recall when that issue was in the news. Boston Public Schools is trying to come up with a map, trying to put a map in their classrooms that shows the various countries and continents realistically relative to each other in terms of their areas. This, by the way, is a version of the Gall-Peters projection, just so we know what we're talking about here. Back to the ESRI article. About a week after these stories started to appear, Tom Patterson, a cartographer retired, began looking at equal area projections to identify an alternative to Gall-Peters. When he didn't find any good options, he contacted Bernard Jenny and Bohan Savrich to find if they would be interested in developing a more visually acceptable equal area world map for schools and socially conscious organizations. So you can see here that we're moving now into the realm of politics and how the visual image of the map is being chosen based on social and political ideas. So these guys are engineers at ESRI, by the way. And they developed something they call the Equal Earth map. The Gall-Peters projection is cylindrical with straight parallels and straight meridians, while the Equal Earth projection is pseudocylindrical projection with straight parallels and curved meridians. So straight and straight. The only way to preserve equal area is to make the spacing of the latitude lines get smaller and smaller as they approach the poles, so that these rectangles, which are in fact sort of trapezoidal shapes on the globe, reduce in area as they approach the pole. So it gives an extreme distortion to the north-south distances. The equal Earth projection, on the other hand, maintains the same distances between the latitude lines, so you're not getting quite such an extreme distortion of north-south versus east-west distances. While being an equal area map, it's a much less distorted in terms of north-south versus east-west. At first glance, equal Earth projection seems similar to the Robinson projection. Both projections have similar graticule shape, but on closer examination, the differences between the two become obvious. Unlike the Robinson, the equal Earth projection is an equal area projection. The Robinson is not. It's not too far off, but it's not equal. It shows continental outlines in a visually pleasing and balanced way. I think that's true. The land masses in the tropical and mid-latitude areas are less elongated. We just saw that. And areas along the poles are less flattened and compressed. I won't read you the whole article, but all in all, I think it's a good representation of some of the issues around mapping, with a little side note of poor science reporting on the part of some of the media in 2017 that were happy to make this false statement that the Gall-Peters projection was the only equal area projection that shows land features at their true relative sizes. It's not. And there are many others that work better. Unfortunately, not an uncommon occurrence in how much of science is reported in the media. Sometimes the folks in the media aren't as up to date on their science as they could be. I'm not bashing media here. I'm just saying that, we can always do better. Anyway, let's go back and look at our lovely Mollweide projection one more time. And I will leave you with this and a bit of music. Have a wonderful day. This is FE Peer Review, signing out.